Hello out there and welcome. I'm Torgersen and I'm the lead designer of C#. And today we'll be talking about C# 11. Nowadays we're shipping a new version of C# every single year in November along with .NET. And this time around it's going to be C# 11. So I'm just going to go right in and show you a bunch of the lovely features that we'll be adding to C# and that hopefully will make your day bright and lovely. So just lean back and follow along here. I'm right in to Visual Studio here, and I have some very simple code, like very, very simple. I have a little method that will take an array of integers. It will go around in a loop and add them up. Couldn't be simpler than that. And I'm passing in an array of integers. So what I'm going to do next is a little magic trick. So I'm going to take this method and I'm going to make it generic. Let's take a t, return a t, take an array of t's, accumulate in a t, and obviously this isn't going to work because t's don't just have pluses and they don't just have zeros, right? So I'm using operators, I'm using literals and so on. That ain't gonna work. But let's see if we can get a little closer. So let's put a constraint on t, where t is an I number of t, which is a new interface we're adding in .NET 7. And now, lo and behold, a magical thing happened. The plus now no longer has a red squiggle, which means, of course, since we trust Visual Studio implicitly, that it will work. So somehow this interface is making plus work. Now, 0 really is an integer. But maybe we could go and look around on t and see, is there something here we can use? And it turns out that, unlike what you're used to, the type parameter here actually has a bunch of static members on it. There's one right there, it's already highlighted. That's probably the one I selected last time I was in here, called additive identity. Well, that sounds like the kind of thing we want as our default value, right? The thing that you start with when you add things up. And now, everything seems to compile. I'm calling the method with an array of ints, so presumably the type argument, yes, the type argument is int. So this should go through and all work with the ints just like before. Let's actually run it and see if I'm right. Otherwise, we're going to take the video one more time. I was right. So there's 15, which is the sum of all those ints. So the method works just as before, but with the important difference that I abstracted completely over what kind of numeric value it's working for. So if we go and change these to, say, doubles, like I can easily do that by just making one of them a double and the rest will convert. Now you can see I'm calling the whole thing with double. And when I run it, indeed, it's going to add them up as doubles. And I could do this with many, many other built-in types in .NET that are all numeric enough that they satisfy this, this INumber interface as a constraint here. But how does that work? Like, how does that put pluses and everything into, interfaces? They're about instance members, right? And operators are static. And what's going on here? Well, the best way to find out is to go and take a look. So let's go and take a look. So here's INumber. And you'll notice that it has a lot of things on it, but it also has a lot of other interfaces that it implements. So it is essentially sort of the nexus of a bunch of interfaces describing individual numeric behavior. One thing you'll already notice down here is something strange, is that this interface has static abstract members, like static and abstract. And that's the new thing here. Static abstract members and interfaces is the feature, the language feature that we're talking about. And with that feature, we've gone and implemented a whole hierarchy of interfaces to represent various numeric things, because you see all these interfaces here represent various aspects of numeric behavior in C#. I'm just scrolling randomly here because see how big the scroll bar goes. Here's I-unary negation operators and I-unary blah, 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 blah. And it has a t-self parameter which represents, the implementing type itself when used in these different operators. You can see the t-self operators show up here. That's the type of the thing that will eventually implement the interface. Let's go and dig into one of these interfaces. Here's I-addition operators. There we go. I-addition operators, all that is an interface that, that has a static abstract operator on it. So operator declarations are always static, and usually they're not virtual or abstract. Instead, they provide a body, right? That's just a static member that you declare in a certain way. But now in interfaces, you can declare them abstract. And what that means is that this operator declaration isn't actually for the interface itself, but it's telling all the implementers that they need to implement this operator. So it's forcing implementers of the interface to implement the operator, either explicitly or implicitly as usual. And then on the other side of things, it promises that when you implement this interface, or when you use this interface as a constraint, as we do here, then the type parameter in question will now have these static members on it. So here we're dotting into a static property, and down here we're applying an operator to, which is also a static member, to values of type t. So that's really sort of the big deal with this. There's also, there's one more, if we can go back to iNumber there. There's one more interface there I want to dwell on for a second. I think these are in alphabetic order, so we should be right around here. This one here called IParseable. So that is an interface, again, with some static abstract members on it that implements the parsability of a type. So this shows a different side of the power of static abstract members, that you can say that something that implements this interface can be parsed from a string. So that means you can't have this as an instance member because the value that we're creating isn't there yet. It has to come from a string and become the type that this interface is being implemented by, right? So here it's a parse method, takes a string, possibly a format provider, and parses that to whatever type is implementing this. And when you think about what this is really a factory, right? This is an example of a thing that you can use static abstracts for, a factory that produces new members of a given type. But this factory is abstract, but it's also static, right? So there's these two patterns, static factory and abstract factory, that many of you are familiar with, actually combined into one and giving the flexibility of both at the same time. So that is all the good news about statics and interfaces. You can use them directly for your own purposes, or you can go and use this wonderful and very comprehensive numeric library. Of course, the implementers aren't limited to our primitive types. Like, your own numeric types can now implement these interfaces and take part in numeric abstraction. And when you think about it, types like matrices, for instance, they have operations on them that in turn make use of numeric capabilities in the underlying type, in the element type of the matrix, right? If you do a cross product, if you multiply two interfaces, you need to do cross products that rely on numeric operations on the elements. Now such data types as matrices can be described in terms of their element type being generic, but constrained to, for instance, iNumber of t, or whatever set of these interfaces is sufficient to implement the matrix level behavior. It's a big new expressiveness, and you can implement your own types and plug in to this whole abstraction mechanism as well. So with that, I'm going to shift gears, and I'm going to go and play with a completely different feature. You know, C# comes out every year now, and there are some feature sets that instead of building a huge, big, you know, Swiss Army knife of a feature in one release, more and more often we'll, you know, take a step at a time over several releases. Sometimes it could be almost a decade where we keep, you know, trickling out new aspects of a feature. And an example of that is pattern matching. So we've been working on pattern matching since C#7, and we have sort of the standard patterns. We had those in place from the beginning, but we keep adding more patterns almost in every release. And C#11 is no exception. In C#11, we are adding what we call list patterns, which is the ability to apply patterns that investigate the list structure, if you will, of an incoming data value. So what I'm actually going to do is I'm going to take this beautiful but very imperative numeric algorithm and I'm going to rewrite it in terms of pattern matching. Okay, away with that. We can write this as a single expression, like proper functional hippies. So we are going to take the values that we get in and we're going to switch on them with a switch expression. And inside of that switch expression, we are going to look at different shapes of input and return a result accordingly. So the first and simplest way to use the list pattern is to say, well, the collection-like thing that's coming in this case an array, has no elements. And if that's the case, well, we're going to just take that t.additive identity and return that. It was an empty list, so we're just going to return whatever 0 is in your data type. And I should use comma here. So the next thing to look at is, what if there's one element? Well, no surprise, that's going to look like this. Here's the element. We're going to recursively apply a pattern, and in this case it's just the var pattern that always succeeds and just grabs whatever value is there into a fresh variable. And if there's one element, well, we're just going to return that. That's the result of summing it up. And we could sort of keep going like that, var t1, comma var t2, and now's the time where we actually get some use out of our plus operator. We would say t1 plus t2. And we can keep going like that, but obviously we don't want to write a case for every possible length of list. So we're going to need to abstract over parts of the list. So let's try something else. Let's say, let's go and use the dot element here in the list pattern. What that is it tells us to take the rest, whatever is the rest of the list here, the array in this case, and return that, apply a pattern to all of it in one fell swoop. So in this case, I can say var rest here and get an array back instead of just a single element. So I'm just getting the rest of it here. And it doesn't have to be the last thing I'm doing. I could say var t2 here, and this would be the middle. And we could describe the result of that as t1 plus recursively call add all on the rest, and then plus t2. Whoop. It was called middle now, so I got an interesting completion there, plus t2. So I can do that as well. Oh, I'm saying 2 instead of t2. There we go. So applying, that just shows you how type checking is your friend here. And we're going to come back to that because the way that I'm using, obviously I'm covering all the cases now. If you noticed before, there was sort of a warning on the switch that I wasn't covering all the cases, all the possible cases, and it's saying, for instance, a pattern of length, a list of, or an array of length 3 or more would not be covered. So it's telling me that, but when I put that one in, I'm handling everything. And also, as per usual with patterns, if something is redundant, then I'll get an error. So in this case here, if I move the more general catch-all here that takes 2 or more above the one that takes 2, then it'll say, well, you already handled all the cases. I will never get to this one. So that works super well. Probably in practice, I would not have written this like that. I would have written it more like this, and it would handle still handle the 2 case. But also, if I move it up further, it handle the 1 case as well. And that is probably, all in all, this is probably the simplest way to write it, where you either have an empty base case, or you have something with at least one element, and then you add up the rest. That's sort of proper recursive list handling using patterns. And this is a very functional language style of doing things. And now in C# it also works super well. So that's list patterns. Now let's go elsewhere in the code and talk about some other things that we have been brewing on. So one theme over the last couple of releases is that we've tried to make structs more expressive. Structs have always suffered from a lot less expressiveness than classes, and to some degree that's warranted, like they can't have inheritance because they're not reference type and so on. But there's some things that are just painful. One of the things has been, let's take this class and turn it into a struct. And what you would have seen up until now is that you would have seen an error on this constructor saying this constructor is not initializing all the elements, all the values. It's not initializing middle name, it would have complained. But you know what? If the compiler is smart enough to see that you're not initializing middle name, why isn't it smart enough to just initialize it for you? So we finally went and took the step after 20 years of C# and said, you know what? Structs should be able to zero initialize themselves just as classes can. They might be smart about it and only zero initialize the things that aren't being initialized in the constructor, or they may do the bulk thing. We don't care. We trust the compiler to do the most efficient thing. But from now on, you don't have to worry about all the kinds of errors you get when somehow there's something you're not initializing from your constructor. And with that, we're going to go turn this back to a class and talk about yet another theme that we've been working on for a while. So we've felt for a while that constructors, you know, they're useful, but they can also be a bit painful for initialization. Like in this case, I have two, just because, you know, I want the middle name to be optional, but optional parameters can only go last, and I want it in the middle because it's the middle name. And so instead, I have to provide two overloads here, and that's already painful. If I were to, you know, declare a derived class, say student, that derives from person, and I'm already in debt because I already have to hook up, even though it's going to generate me a nice null array constructor. I don't have a base one to call, so it's already, you know, driving me to add more constructor madness. And it's just like a lot of code that propagates, and whenever you make a change, you have to propagate that change up through your constructors and so on. And that's painful. So we've generally, over the last couple of releases, tried to be more supportive of an approach where you do not use constructors for initialization and use object initializers instead. Like, both are fine, but we want to make the object initializer choice better. And so so that when you go and, let me just delete the code here so we don't have two sets of top-level statements. If you go up here and say, you know, var meds equals new student, first name equals meds. The first problem we had, and that we solved a couple of releases ago, was, well, you can't have immutable work very well with object initializers because they need to assign things. And what we introduced was a version of the setter called the init, so that you couldn't, it's a setter that can only be run from the object initializer, and after that, you know, the object becomes immutable. So that took care of that problem. We still have a few things left where constructors kind of have us beat in terms of this, and that is that there's no way that I can require that an object initializer initializes certain members the same way that I can with a constructor, simply by having those as parameters in the constructor. And that is something we're going to fix in C#11. I don't have that working yet, but I'm just going to show you anyway what it's going to look like. But first I want to point out that these warnings that we have here, they're about the fact that you have a non-nullable property, and it should be non-nullable. In this object model, at least, everyone should have a first name. I mean, you can argue whether that's a good object model, but the way that we've written it, it should not be null, but the default value of it is null. So it's warning us to initialize it. And that's kind of annoying. I don't want to have to say, well, make it null anyway, you know, and forget about it with the bang operator, or make everyone have the name Bob. You know, that's kind of unsatisfactory. So what we are doing instead is to allow you to require fields and properties. So I could say public required. And what that means is that there's no object initializer without first name. And if I do that on the first and last name, then this will now be, this up here will now be an error because you're only providing the first name, but you're required to provide the last name. And the payoff of that is that these warnings, once this feature is actually in and works, these warnings will go away because the required tells the nullable analysis, don't worry, this will get initialized. The creator of the object, the caller of the constructor, will always take care of it. We are going to make sure of that. So that's required members. I think that's going to be super useful, and it's going to help stamp out some of these nullable warnings that people often find when they are not using constructors. Now we're talking about properties. There's another thing that we're also doing that also doesn't work yet. So let me get back to a compilable state. And that is, in terms of auto properties, we've also been sort of improving them gradually, like from release to release, like the init here, for instance. But once you need to do a little bit of work in your property bodies that's not just assigned to a backing field, then you fall off the cliff today, and you have to declare your own backing field, and you have to describe both of your accesses manually, and you're sort of out of the auto property game. And we want to smoothen that ramp out. So what we have now is what we call field access in auto properties. So that means that each accessor gets to, even in an auto property, they get to implement themselves. And when they do so, they can refer to the automatically allocated backing field, which is referred to by the innovatively named keyword field. So I'm going to have to escape out of that because that also doesn't work yet in the preview I'm running on now. So instead of just assigning value to it, which is the default behavior in an auto property, maybe I want to just do a little bit of trimming here. You know, I want to just make sure that the white space isn't there and so on. And now I don't fall off the cliff. My getter can still be auto-implemented if I want, using the same backing field as the one that I'm explicitly accessing here, and everything's good. And with that, I'm going to go talk about the last feature I want to show today, which is what we call raw strings. And for that purpose, I'm going to go away from Visual Studio and into this little tool written by community members called SharpLab. The nice thing about SharpLab is that you can see the output of the program right over here, and that's going to be very useful for this demo here. So it's a long-standing problem that if you have some sort of code, some sort of, like, it could be JSON or XML or program code in any language, it's very likely to have things in it that can't just be written inside of a string literal in C#. Like, it'll have quotes, double quotes, it'll have backslashes and all kinds of stuff. So we want to try to solve that problem once and for all. So how about a form of string literal that has no escaping in it whatsoever? That's what we call raw string literals. And the way you declare a raw string literal is like a string literal, except with more double quotes. So in at least 3. So in this case, now you can see that the content is printed verbatim over here. The backslashes are now part of the content, not escapes. So I'm going to just remove those because the whole point was to have those quotes correctly displayed. Now, what if I wanted double quotes, or double quotes are fine. What if I wanted triple quotes in my content? Well, now we have a problem again, but I can always add more quotes at the beginning and the end of a raw string. And by doing that, I can always, there's always a way that I can defeat however many quotes you have in the code that you copy pasted in here or want to have verbatim in there. I don't want that right now, so I'm going to go back and to the state we were in before. Now, oftentimes you want these to be multi-line, and for raw string literals, when they're multi-line, you have the content separately from the delimiter. So you have to have a new line right after the beginning and right before the end delimiter here. Now I'm in a multi-line one, and I can start, actually using multiple lines, and you can see on the output over there. Something interesting is happening on the output, which is that even though I have white space next to my content here in each line, the white space doesn't show up in the output. So you know, let's try to do a little bit of indentation within the content. And you see that white space is there. And so what is going on here is that we have some mechanism for ensuring that we can remove leading white space, which means that when your literal occurs inside of code that is you know, deeply nested, you don't have to have the literal all the way, you know, flush all the way to the side and kind of break with the indentation flow of your code. But what if you don't want to eliminate the white space in front? What if you actually want to keep it? Well, it's actually the end quote here that decides how much white space you get. So the further I move this to the left, the more white space becomes significant. Essentially, the end quote here decides the line where we cut. Everything to the left of that gets cut on every line. So that is pretty smart. Now let's get it back out where we cut all the white space. One last thing is that sometimes, you know, curlies are fine in here as well. They're just part of content. But sometimes you do want to interpolate, and you can have interpolated raw strings as well, in which case you put a $, and now single curlies become delimiters for interpolation holes, just like in interpolated strings today. And that's great, you know, but what if you want curlies in content? We said we're not going to do any escaping, and we're going to stick to that. Well, what you can do, so I'm not allowed to put, if I put two curlies, that's going to be an error here. But what I can do is that I can put more $signs in front. And the number of $signs I put, I need to click in the right place. The number of $signs I put in front is the number of curlies it takes to delimit an interpolation hole. And any number of curlies less than that is content. So if I put just single curlies out here, they're just content. And I can even put single curlies around my interpolation hole, and they're content as well. It's just the innermost ones here, the innermost two become the whole. So that's raw string literals for you. And that's also the last C# feature I wanted to show you. Now I just want to go to a few places where you can find out more. We actually, many of these features, you saw them working. They will work for you as well if you use the preview language version in the releases of C# that come out with versions of Visual Studio. And every time we do a new preview with new language features added in preview, Kathleen here is going to put out a blog post on the .NET blog. Here's the latest one as of this recording, and that's going to introduce you to whatever new features are available for you to try out, so that you can give us feedback and we can adjust, and we have done extensively already based on the feedback that we get from that. If you want a little more detail other than the sort of the quick introductions and examples here, we also track new features even in preview on the docs pages of the C# docs pages that Microsoft has. So here's what's new in C# 11, and it describes all the features that are in there so far. And finally, if you want to follow the whole making of the sausage in where we actually design the language, you can go to our GitHub site for C# language design, which is .NET C# Lang. That's a much more rowdy place, and it's harder to find your way around. But oftentimes you can get links from these places here that'll take you into the right place if you want to know more. And with that, I'll send you on your own journey to play with these new language features as they show up. And look forward to C# 11 when it becomes official, and you can all start having some raw strings in C# 11. Thank you very much.